everyone. Welcome back in this video lecture series on refrigeration and air conditioning. I am Mayank Kushwaha from ABES Engineering College is discussing the Unit 3. And in this video lecture series, we have discussed in the last lecture about a refrigeration system working on reverse Carnot cycle. We discussed that although Carnot cycle is the best cycle, which gives the maximum possible efficiency of a system working between two temperature ranges. But even then, we cannot use this cycle to manufacture any device. And the reason of the same were also discussed. So, but then the obvious question that comes to our mind is that what is that thermodynamic cycle on the basis of which our refrigerator and our air conditioning systems are working? So this is what we are going to talk about in today's lecture. And the answer to that question is vapor compression refrigeration system. In short, it is called VCRS. So vapor compression, as you can see here, this is a cycle where we will be using vapor form of a liquid, which will be used for the absorption of heat from the space to be cooled down. So to understand this, let me draw the line diagram first. So I would say that the first part is the device which enables a cooling medium to absorb heat. And the name of this device is evaporator. Then that the same cooling medium is supplied to compressor. Next important device is condenser. And finally, an expansion device. Right? So this is a usual basic diagram to study a vapor compression refrigeration system. So what actually happens, a cooling medium, which is a refrigerant, which refrigerant, most commonly refrigerant which is used nowadays is R134A, which is nothing but C2H2F4. So hydrofluorocarbon, I'm sure you must have heard about this. More recently, a new refrigerant is being utilized in all practical devices, all commercial devices, which is R32, CH2F2, difluoromethane. So these are two most used refrigerants. So what actually happens? This refrigerant is supplied here, which is usually in liquid form. As this liquid refrigerant passes through evaporator, it absorbs latent heat of evaporation from the objects to be cooled down, as a result of which it gets converted into vapor form, then this vapor gets compressed in a compressor, usually a reciprocating compressor, and it gets converted into a superheated vapor. Superheated vapor. Then this vapor rejects heat. This vapor rejects heat. QR. I'm sure you are familiar with the terminologies QA and QR, which we have been using for a couple of lectures. QR is nothing but the heat rejected to the surrounding, right? So this superheated vapor reject this heat QR in the condenser, and it again gets back converted into liquid form, or most of the time liquid plus vapor form. Finally, this liquid plus vapor gets expanded and cooled down to liquid form so that it can again be utilized for the absorption of heat in the evaporator, right? So you can see from here that the vapor is getting compressed. That's where the name of this system is derived: vapor compression refrigeration system. And the vapor of what gets compressed is refrigerant, which flows in this system, right? So this is the cycle which we use for on the which all our refrigeration devices are made. Okay. For the analysis purpose, let us try to draw it on thermodynamic cycles. So the most common coordinates which we use to show a VCR system is pH diagram, pressure enthalpy diagram, as well as temperature entropy diagram. I'm sure you are familiar with two-phase regions. So on pH diagram, the dome of two-phase is represented by this curve, whereas the corresponding two-phase diagram on TS diagram is represented by this curve, the bell curve. To represent the cycle, we draw it like this. There are many ways to draw. One of the most simple, most basic way of representing it is this. I will tell you the name of the process a little later. Process 1, 2, 3, 4. And the corresponding processes on TS diagram are somewhat this. Process 1, 2, 3, 4. To name the processes, we can write process 1 to 2 is, you can see the entropy is constant here. So it is isentropic process. Isentropic compression. Process 2 to 3. From here, you can see the pressure is constant. So this is isobaric condensation or heat rejection. 3 to 4, as you can see here, enthalpy is constant. So in 3 to 4, you would see enthalpy is constant. So this type of process is called isenthalpic expansion. 4 to 1 process is, as you can see, the pressure is constant. So it is isobaric evaporation or heat absorption, right? So what is happening here? This is the process 4 to 1 in which heat is absorbed. This is the process in which heat is rejected. And this is the process where work is being supplied into the system, right? So from our understanding, we know that of thermodynamic system cycles that refrigerating effect, which is nothing but QA, which is involved in process 4 to 1, can be given by H1 minus H4. Work supplied WN involved in process 1 to 2 can be given as H2 minus H1. Similarly, heat rejected involved in process 2 to 3 can be given as H2 minus H3, right? So the COP of a refrigeration system based on VCRS can be given as refrigerating, which is the basic formula, refrigerating effect divided by work input. So this can be given as H1 minus H4 divided by H2 minus H1. Right? And this is a very important relation which will be used in further lectures to calculate the COP and solve a numerical based on VCRS system. Okay. These are some of the references which I have followed. Thank you.